Okay, welcome everyone to regular Simon Center for Geometry and Physics weekly talk, but this talk is special. It's the first talk of Della Pietra series of lectures. As you might know, due to the generous gift by Della Pietra families, we have this Della Pietra series of lectures, which each consists of 3 lectures. Today is the first colloquium for scientists and mathematicians, and tomorrow there will be 2 more talks, one for high school students and freshmen undergraduates, I guess, this time, and the other one will be public talk. And all of these 3 talks will be given by our distinguished visitor, Professor Charlie Kane from the University of Pennsylvania. Charlie is known for his breakthrough contributions to theoretical condensed matter physics. He received his PhD in 1989 from MIT, and after postdoc at IBM, he joined the University of Pennsylvania in 1991. He's there, and his work was recognized with many prizes: Breakthrough Prize, Buckley Prize, Gerard Prize, and he's mostly known for jump-starting the whole theory of topological phases of matter by extending stuff known in lower dimensions to 2 and 3 dimensions. So I'm really pleased to introduce Charles. Please.
Okay. Well, thank you very much, Sasha. And
sorry, just one more thing. That's our standard souvenir from the Simon Center.
Oh, wow. Wonderful.
Expositor talks.
All right. Thank you. Okay. Well, it's really a pleasure to visit. I'm visiting here for the week, and I'm already having a great time at the Simon Center. So thank you for hosting me. And so what I'd like to do is tell you a story today about symmetry and topology. And so symmetry and topology are sort of conceptual pillars for how we think about matter, how we think about physics. And so symmetry is the most familiar of these. This is something that we start off. I'm teaching freshmen right now, and so we teach our freshmen. You always think about symmetry because symmetry makes things simpler. And so what symmetry is about is it's about what you can do to a system that keeps it the same. Okay, and so if you look at these beautiful pictures, you can translate them or you can rotate them, and the pictures still look the same. And by understanding all the symmetries that a system has, that gives you tremendous power in understanding the system. Okay, and in particular, it allows you to think about conservation laws. And there's an important thing, which goes back to Landau, which is that understanding the symmetries of a system allows you to distinguish phases of matter based on the patterns of symmetries that they have or that they break. Okay, and so for instance, in these pictures, in a crystal, you have a sort of a discrete lattice translational symmetry or rotational symmetries, and so that allows you to sort of classify phases of matter. Now, so symmetry is very powerful, but there's another idea, which is topology. And what topology is about is, what can you do to a system that keeps it the same? Okay, so what is it that stays the same when you deform a system? And the sort of classic example for topology is explaining the sense in which a donut is the same as a coffee cup. Okay, you can imagine if they were made out of clay, you can imagine smoothly deforming one into the other. The hole in the donut turns into the handle of the coffee cup, but it's not the same as a sphere, because in order to get from a sphere to a donut, you'd have to poke a hole in it. Okay, and that's against the rules. And so of course, topology is a very deep and beautiful branch of mathematics. But it has application to physics, which is of matter, and so that's what I want to focus on today. Now the sort of application of topology in physics it goes back many decades. Okay, and so this has been around for some time. What is a little bit more recent has been our understanding of the interplay between symmetry and topology, and understanding this interplay between symmetry and topology has led to a sort of a new, deeper understanding of the kinds of electronic phases of matter that can occur. Okay, and so that's what I want to describe to you today. So I'm going to sort of start off with a little bit of an introduction, just to try to explain how it is that this sort of abstract mathematical idea of topology applies to electronic systems, and in particular the band theory of solids. And so that'll lead me to do a discussion of topological insulators and topological superconductors, and then I'll close with some closing thoughts about sort of where the field is and where we're going and what the frontier is. Okay, and so I started off working in this. It started off with my colleague Jean Malie at the University of Pennsylvania, and then over the years we were joined by many students and postdocs and other colleagues, and so much of the work I'm going to be describing that I contributed to was with these people. Okay, so I want to talk about phases of matter, and so to begin with, I'd just like to start with the most basic phase of matter, the most basic electronic phase of matter, which is the electrical insulator. Okay, and again, I'm teaching freshmen now. I tell them what an insulator is. So what you say in an insulator, the electrons are stuck. They're bound to the atoms. They can't go anywhere, so an insulator can't conduct electricity. Now, actually, what I don't tell my freshmen, but is true, is that this fact is actually a unique consequence of quantum mechanics. Okay, so how can the electrons be stuck? Well, they're stuck because quantum mechanics quantizes the energies that you can have in an atom. And so if you have all the occupied orbitals separated from the empty orbitals in an atom, then the atom is completely electrically inert. Okay, the electrons can't do anything. So you can sort of say the electrons are all stuck. It's like the insulator is the most boring state because the electrons, they don't do anything. Things get a little bit more interesting if you allow the atoms to interact with each other more and form covalent bonds. And, it was really one of the great triumphs of quantum mechanics in the last century was sort of describing the language for how we understand the electronic properties of these sort of covalent insulators, like semiconductors. Right, and this language, which is the band theory of solids, is probably the most consequential theory that we have in physics because it allows us to get a very, very detailed understanding of the electronic properties of very important materials like silicon. Okay, and let me just say, it's complicated. There are lots of there's a conduction band and a valence band, but there's a sense, the occupied states are still separated by the empty states by this energy gap. So there's something that sort of stays the same between these two. And so the point that I want to make is that there's a sense in which this complicated covalent insulator is kind of the same as this completely trivial atomic insulator, because you can imagine sort of smoothly deforming one into the other, smoothly pull the atoms apart and have one sort of cross over from this picture to this picture. So there's a sense, in the sense of topology that I introduced before, there's a sense in which these phases are continuously connected to these phases. To these. So there's a sense in which they're the same. Actually, it's kind of the same as the vacuum. The vacuum, of course, isn't as empty as you might first have thought, at least if you think in terms of relativistic quantum mechanics. Dirac's theory of quantum mechanics, the vacuum has a valence band too. Okay, so you can have electrons, but you could also have holes, which are like removing particles from the valence band. Okay, and so the positron, the antiparticle of a hole of the electron, is really just like a hole in a semiconductor. Okay, and the only difference is that this energy gap is 1,000,000 times bigger. So there's a sense in which all of these are really kind of the same. And so I'd like to elevate this to a principle, which is that insulators are equivalent if they can be continuously deformed into each other without closing the energy gap. Okay, and most insulators are sort of like the trivial atomic insulator, sort of like the sphere. Okay, and so once you phrase it in this way, then it poses the question: could there be topological phases that are different from a trivial insulator? So in pictures, if the trivial insulator is like the sphere, then is there an analog of the donut? Okay, and the remarkable answer to this question is yes, topological phases are possible, and they're fascinating phases of matter, and that's what I want to tell you about. Okay, so to sort of get started on this and to give you a flavor of what these topological phases can do, I want to give you the very simplest version of this, which is a topological electronic phase in a one-dimensional system. Okay, and the one-dimensional system that I want to consider is a conducting polymer called polyacetylene. And what polyacetylene is it's basically a chain of carbon atoms with hydrogen atoms attached. And the thing that's interesting about this is if you form sort of a perfect chain where the atoms are all evenly spaced, then it is actually an electrical conductor. So you have basically a half-filled band, and it's an electrical conductor. But this is not what polyacetylene wants to do. So what polyacetylene would rather do is it would rather sort of pair up alternating atoms. So to make the atoms a little bit closer together. So there's a distortion where the green atoms move to the left and the blue atoms move to the right. And then what that does is it opens up an energy gap. All of the occupied states go down, so it lowers the energy. Okay, and so real polyacetylene is an insulator. Okay, it has an energy gap separating the occupied states from the empty states, but it's kind of an interesting insulator because there are two ways you can do it. You can either have your bonds alternating, strong, weak, or they can alternate weak, strong. Okay, and the direction of the distortion is sort of opposite in these two cases. Okay, and so what I'd like to argue to you is that these two insulating states of polyacetylene are topologically distinct in the sense that I told you about. Okay, because if you tried to go from this to this, you have to go through U equals 0. And U equals 0 is this, which is not the insulator. Okay, so you can't get from this to this without going through a quantum phase transition where the energy gap closes. Okay, and so one can ask the question: so how can we, if these are distinct, how can we characterize them? Is there some analog of the genus that counts the number of holes in the donut? Is there some topological invariant we can use to distinguish these? And so there's a simple way you can formulate the topological invariant that distinguishes these. If you write down the simplest model for polyacetylene, which is basically there are two atoms in every unit cell, so one can write down a model that is just a two-band model. Okay, so there's just one conduction band, one valence band. So your Hamiltonian as a function of momentum is just going to be a 2x2 matrix. And you know that 2x2 matrices can be always combined to be written in terms of the Pauli matrices. Okay, and so now it turns out that in polyacetylene, this so it's sort of like a magnetic field. This magnetic field is always in the XY plane. And so one can characterize this by a winding number, which counts the number of times this field h of k winds around the origin as a function of momentum. Okay, so either it looks like this as it's not wrapped around, or this, or it's wrapped around. So it could wrap around any integer number of times. Okay, and that actually distinguishes between these. Now I have to be a little bit honest here. I put a little star. There's a caveat. Okay, which is a phase says I'm really assuming the presence of some symmetry. Okay, because if I think about it in terms of this Hamiltonian, of course I could have a z component to my field, in which case I'd be able to take this and sort of take it above the origin and continuously get from this to this without doing it. Okay, so there's something that prevents the z component, and so there's actually this simplest description of polyacetylene actually has a little bit more symmetry than than real polyacetylene has. And in particular, it has a kind of interesting symmetry, which is that in the simplest description, the conduction band and the valence band are exact mirror images of each other. Okay, and so we call this particle hole symmetry. An electron in the valence band is sort of symmetrical with the hole in the valence band. So if you take energy to minus energy, this sort of looks the same. And that symmetry, now that symmetry is not a real symmetry of real polyacetylene. Okay, but it's very interesting to think about the consequences of this symmetry. And this symmetry will show up a little bit later in this talk as a real intrinsic symmetry of something. So it's useful to think about this particle hole symmetry. A symmetry that polyacetylene actually does have is C2 rotational symmetry. If I just rotate by 180 degrees, then this picture stays the same. And that symmetry actually is enough to protect the topological distinction between these two phases. Okay, so polyacetylene really does have two phases, but you need to invoke symmetry in order to say that. Okay, so now, the thing which is really important about this, though, is the consequence of these topological phases, and the most important consequence is what happens at the interface where these two topological phases meet. Okay, and so what this leads to is topological boundary modes. And so if you think about this, and so this is sort of physics which was really sort of discovered first, I think, by the field theorists, Jakiv and Rebbe, and then it was also sort of independently discovered by Sushri Verheeger, who were thinking about polyacetylene, and then at some later time they sort of got together and realized they were talking about the same thing. Okay, and so in the field theory context, if you think about a one-dimensional, well, actually, let me talk about polyacetylene first. So it's easy to understand in polyacetylene why, if you have the A phase meeting the B phase, so if I think of these bonds as being really strong and the weak bonds as being really weak, then it's clear you're going to have a big gap. You're going to have the two states are going to split a lot for these dimers, but then this one is going to be sort of left behind, not talking to anybody. And so this is your zero mode. Okay, it's at zero. Now, you could ask the question, well, what happens if I turn up the weak bonds a little bit? And here's where the particle hole symmetry is a very useful conceptual tool, because you see what the particle hole symmetry guarantees is if there's a state at positive energy, it has to have a partner at negative energy. Okay, and now this zero mode, when I turn these bonds off, then I have this zero mode here. So now when I turn it back on, I can ask, well, what happens to it? Well, nothing can happen to it because this guy is exactly at zero. It's its own partner. So there's no way it can move away from zero, because then its partner would have to appear out of nowhere. Okay, so this zero mode is topologically protected given this particle hole symmetry. Okay, and so it can't go anywhere, and so this is the zero mode, in polyacetylene, and in field theory one can understand this zero mode as arising when you have a one-dimensional Dirac Hamiltonian, and basically without the mass term, it describes a one-dimensional electrical conductor, and then this is the mass term which opens up an energy gap. And what Jakiv and Rebbe found is that when the mass changes sign, which is precisely what happens when you go from the A phase to the B phase, then at this domain wall where the mass changes sign, there's a very simple exact solution to this Hamiltonian. And for the students in the audience, if you haven't been through this calculation, showing a satisfying calculation to understand. Okay, but in any case, so one has this sort of zero mode, no matter what the profile of the mass term is. There's an exact zero mode, and so this is sort of the consequence of the boundary. Now, there's an important point that I want to make, is that there's sort of two levels that you can understand this phenomenon on. Okay, so there's the sort of single particle level where I'm thinking about the eigenstates of a sort of single particle Schrodinger equation, where you have eigenstates which are in the conduction band, eigenstates in the valence band, or maybe you have an eigenstate which is this zero energy eigenstate. Okay. Now, but of course, the real system that we're interested in thinking about, say if it's polyacetylene, is a system that has lots of electrons. Okay, and usually we fill up all of the valence band states with electrons, and then maybe this is filled or not. Okay, and so in the many-body context, then this phenomenon actually leads to something that's really surprising the first time you see it. So it leads to charge fractalization. You see, because you know that so this zero mode, it can either be occupied or empty. Okay, but because of the particle-hole symmetry, those two states have to have opposite charge, which means they have to be either plus E over 2 or minus E over 2. They differ by E, and they have opposite charge. And so what happens is that there is a precisely quantized charge E over 2 at this boundary. Okay, so it's as if the electron is split in half. So if you imagine if you're in the middle of the A phase, you can add an electron, and that electron can then split into two charge E over 2s with the B phase in between. Okay, and so so in the many-body context, what we're really doing here is we're splitting the indivisible. Okay, so we have an electron. You can't really split an electron in half, but you can split an electron in half with the aid of a topological phase in between. Okay? All right. So what I want to show you is that there are many, many more examples of this kind of phenomenon. Okay? On some level, what they all amount to is taking something which is indivisible and splitting it in half.
So what does that mean, really?
What does that what?
What does that mean, really?
What does it mean? It means that if you were to measure the charge here, there's a sharply quantized charge E over 2. Okay?
The uncertainty of quantum mechanics or something like this?
No.
What allows it?
What allows it is this topological phase that's in between. So, yeah. So now, look, I'm not saying that there's half an electron. There are lots of electrons. Okay? So the charge that we're measuring is
Measure.
Yeah, no, but the thing is, if you were to go in with with something that measures the electric field, you measure the electric field, what you would measure is an electric field due to a point charge of E over 2. Okay. I mean, if you didn't have anything, then basically it's electrically neutral. Okay, so there's no, even though there are electrons, but if you step back from it, sort of you're further away than the distance between the electrons. It's basically perfectly electrically neutral. But this thing by itself has a point charge, okay, and that point charge has a size of E over 2. It's not a single electron or anything that's doing it. It's a sort of collective behavior of all of the electrons, okay. But the thing that's truly remarkable to me, at least, though, is that this E over 2 it really behaves like a particle. Okay, it's not the original particles you started with. Those were electrons and protons, but it's an emergent particle. And the story of this is that emergent particles can have properties that are unlike the original building blocks, and that's one of the fascinating things that these phases of matter allow us to have.
Does the many-body ground state have charge E over 2? Is that what that means?
Well, no, what I mean is that there is a charge E over 2, in the many-body ground state, there's a charge E over 2 localized. I mean, of course, the thing is made out of electrons, so the ground state has to have an integer number of charges. But the thing is, I can spatially separate these charge E over 2s. I mean, of course, now you can't have it. All right. Okay, so I want to give you another example of splitting something that's indivisible. Okay, and so what I want to think about is a one-dimensional electrical conductor. Okay, and so this could, for example, be this undimerized polyacetylene. Okay, which and I can think of it as energy. It has filled up to a Fermi energy. It has It has electrons which are moving to the right at the Fermi energy and electrons which are moving to the left at the Fermi energy. So I can call these, if I look at low energy, the low energy excitations are near the Fermi energy. They consist of right and left moving chiral fermions. So all that I mean by chiral fermion is that this right moving electron is moving to the right. Okay. Now, of course, a one-dimensional electrical conductor is a kind of a fragile thing. Okay, if you introduce a periodic potential or you introduce disorder, then it'll become localized. Basically, your electrons, which are moving to the right, they're going to bounce off of something, then they'll come back to the left, and they're going to be constantly sort of bouncing back and forth, and they never get anywhere. Okay, and so that's what happens if you put on for instance, a commensurate periodic potential. Then what happens is you open up an energy gap. Coupling together, by coupling the left and right movers together, and that turns it into an insulator. Okay, and so this is a trivial thing. So now, so this is a real problem for making, small electrical devices. If you have a one-dimensional conductor, it's a very fragile thing. Okay, and so wouldn't it be nice if we could figure out some way of making it less fragile? And so what I want to show you is that it's actually possible to split this in half, okay, and to spatially separate the right movers from the left movers, okay? And the way I'm going to do it is going to be kind of similar to what I did with this Schrieffer-Heeger, with polyacetylene, okay? So what I'm going to do is I'm going to take a two-dimensional system that is just a whole bunch of copies of this one-dimensional insulator where on each wire my right and left movers are sort of coupled to each other, bouncing back and forth. Okay, but what I'm going to do is in the middle here, I'm going to make it so that the right mover on this wire, instead of backscattering on the same wire, it backscatters over to the next wire. Okay, so I'm going to make it look like this. Okay, so on these inside here, what I'm doing is I'm locking my right movers with the left movers on the next wire. Okay? And so this, of course, makes a kind of an insulator too. Okay? But I want to argue that this is a topological insulator. And so the thing that's interesting about this is if I look on the boundary between the topological insulator and the trivial insulator, there's one edge mode that gets left behind. Okay, so in the same way that in polyacetylene I took an electron, I split it in half. Here what I've done is I've taken a one-dimensional electrical conductor and I've split it in half into two chiral conductors. There's one that propagates only to the left and one that propagates only to the right. Okay, and so this this is pretty nice, okay? And these one-dimensional conductors, these chiral one-dimensional conductors, are very special things because, if you're an electron in one of these, you have no choice but to keep going forward, okay? You don't suffer from this problem that if you run into any little piece of dirt, you get backscattered. These are going to be immune from localization, okay? And so these chiral edge states, which exist on the boundary between a quantum Hall state and an insulator. So this is what we call a Chern insulator, quantum Hall state. There's sort of like a one-way street for electrons. Okay, and if I think in terms of the dispersion, there's the states, they only propagate to the right. Okay, so it's just going to go one way. Okay, and again, just like with the polyacetylene, there's sort of two levels that you can think about this on. You can think about it on the single particle quantum mechanics level, where there you have a spectrum of eigenstates which connect the valence band to the conduction band like this, and these are the states which are the single particle to right. Okay, but you can also think of what the many-body ground state looks like. And so there in the many-body ground state, you fill all of the states with electrons below the Fermi energy, and then you have a Fermi energy here. And the low-energy excitations on this Fermi energy, near the Fermi energy, then are described by basically a free chiral Dirac fermion. Okay. And this free chiral Dirac fermion has very sharply defined, robust properties. One property is its quantized electrical conductance. So if you were to raise the Fermi energy by a certain amount, then you have more current flowing to the right. Okay, and that defines a quantized electrical conductance, quantized in units of E² over H. And in addition, if you were to have these, these edge states, and you raise the temperature a little bit, then there will be more heat flowing down the edge, and that defines a quantized thermal conductance, which is also quantized in some other units. Okay, and so these define sort of fundamental characterizations of the many-body ground state of this chiral system, and in a sense these it's impossible to have this in isolation. Okay, and one so there has to be the left mover somewhere else. Okay, and the fact that this cannot exist in isolation. One way of summarizing that is to note that this free chiral Dirac fermion has an anomaly. It has a chiral anomaly, which is related to the quantized electrical conductance, and it also has a gravitational anomaly, which is related to the quantized thermal conductance. Okay, and so this is sort of a very fundamental thing that this chiral edge state has. Okay, and so you can ask, well, how can we have this? And so let me, this is the quantum Hall effect. But let me just say in this simple picture what's going on here. If you think about what the electrons are doing, they're localized, but they're kind of going around. They're kind of going around in a circle. It's sort of like a Landau. It's sort of like cyclotron motion. Okay, and so really one way to make this happen is to have electrons undergoing quantized cyclotron motion, and that's precisely what the quantum Hall effect is. Okay, and I'm telling the story backwards, of course. The physics of this was actually first discovered experimentally in the laboratory, on some crappy-looking sample like this, right? It doesn't look very perfect. But you measure a virtually perfect quantized Hall conductance. Okay, and amazingly, this quantized Hall conductance, you can measure this integer in this quantized Hall conductance, which is really this. Okay, you can measure that to a part in a billion. Okay, it's really amazingly even in an imperfect, dirty sample. Okay, and now, this is a little bit old physics. This is all from the 1980s. Okay, and it was experiments like this that sort of initiated the thoughts about topology applied to condensed matter physics. Okay, but just to show you that it's actually not a completely closed subject. It took almost 40 years later before we had the similar measurement of the quantized thermal Hall conductor. That only happened in the last few years, and this is an ingenious experimental method to, it's actually kind of hard to measure the thermal conductance. Okay, this experiment done by Moti Heiblum at the Weizmann Institute seems to have nailed that. Okay. So the easiest way to make this happen is in a two-dimensional electron gas in a perpendicular magnetic field, the quantized Hall effect. But as this example suggests, maybe a magnetic field isn't necessary. Maybe what you need is just you have to break time reversal symmetry. You have to make it so the electrons know which way to propagate time, but in an ordinary two-dimensional band structure can be characterized by a integer topological invariant, and this Chern number is equivalent to this integer in the integer quantum Hall effect. Okay, so
Would that be related to the fractional effect too?
Well, the fractional effect, there's more to the story in the fractional effect. Okay, so so the Chern number, this is a good way of characterizing something where you have a unique ground state. Okay, in the fractional quantum Hall effect, there's a topological ground state degeneracy, and so one has to develop other methods for talking about that. Yeah. Okay. So good. So. Okay, now, for a long time it was believed that this was really the only kind of topological state you could have. Okay, and it's kind of hard. In order to make this happen, you have to, usually you have to use a big electromagnet in order to make the quantum Hall effect. And so you could ask the question: what if you didn't have a magnetic field? Could there be anything? Okay, and so the more recent progress is that when you do have time reversal symmetry, new things can happen. Okay, and so let me just say a few words about time reversal symmetry. So what time reversal symmetry is about is if you take a motion picture, okay, and then you run the motion picture backwards, you look at it, and so the question is, does what you see obey the laws of physics or not? Okay, and so the fundamental laws of physics kind of do obey time reversal symmetry. Not thermodynamics, of course, but the microscopic laws. Now, but of course, a magnetic field changes sign under time reversal, okay? Because magnetic fields are created by electrical currents, and if you run the motion picture backwards, the current goes the other way, okay? Likewise, if I have these chiral edge states, a right mover, if I run it backwards, turns into a left mover. Okay, so it sort of makes sense that you need to have a magnetic field in order to get this to happen. Okay. Now another thing that's worth thinking about is spin. Now, of course, electrons have this uniquely quantum mechanical feature, which is they have spin. So they're like little spinning tops. And under time reversal, in quantum mechanics, time reversal does two things. It actually it gives you a star here, a complex conjugation, and it also gives you, there's a minus sign, okay? And I love this minus sign. This minus sign makes very miraculous things happen. And what it gives you is it gives you something called Kramer's theorem, which is that if you do time reversal twice, then you can see that that the wave function goes to minus itself, okay? And what this tells you is that when you have fermions that have time reversal symmetry, every state is at least two-fold degenerate. Okay. Now, on some level, this is like a trivial effect. This just says that if you don't have if you don't have a spin-orbit interaction, that just says that the upspin states are always the same energy as the downspin states. Okay, and so so in a sense, that's kind of simple. But if you do have a spin-orbit interaction, then where you can't talk about the spin and the sort of orbital degrees of freedom independently, then this has much more richer consequences. Okay, and so one can ask the question, the integer quantum Hall effect sort of required us to break time reversal symmetry. Are there topological phases with unbroken time reversal symmetry? And so what I want to do is I want to sort of play this game of trying to split the indivisible again. But now let's suppose we have time reversal symmetry. Okay, so that means that if I have my one-dimensional wire, it has to have both up and down spin electrons. Okay, so now let's suppose I have this one-dimensional wire. So both right movers and left movers, I have both up spins and down spins. Okay, and so what I want to do is I want to try to split this in a way where after I've split it, it still looks the same when I run the motion picture backwards. Okay, so that's something I can do. And so what I can do is I can split it in this way. Okay, where on the top edge the up spins are going to the right, the down spins are going to the left. Okay, and the opposite on the downside. So if I then the up spins turn into the down spins, and the right movers turn into the left movers. Okay, and so it looks the same. Okay, so this, in principle, should be possible without breaking the symmetry under the reversal of time. I don't need a magnetic field. Okay, Now, so these edge states, we give them a name. They're called helical edge states. And so you have a right mover going to the right and a left mover going to the left, but they're opposite spin. Okay? And so these edge states are both protected. So they're impossible to have in a purely one-dimensional system, and that fact means they are protected by time reversal symmetry. Okay, so so they're protected by time reversal symmetry because there's nothing I can do to this. The only way I could open up an energy, these states cross. The only way I could get them to couple to each other is if I break time reversal symmetry. This degeneracy here is a Cramer's degeneracy, which is protected by time reversal. And so what that means is that it's impossible to have just one of these by itself, right? Because if I could have just one of it by itself, then I'd be able to get rid of one of them. So these helical edge states are sort of very special when you have time reversal symmetry, and likewise they are characterized by some kind of anomaly. In this case, it's a kind of a Z2 anomaly, and the bulk of the 2D quantum spin Hall insulator is characterized by a Z2 topological invariant. Now, in order to get this to actually happen, what you need to have is you need to have something where every state isn't just filled with an upspin or a downspin independently of what state is it. So you need a spin-orbit interaction. And so for this purpose, the best place to look for this is in materials that have a very strong spin-orbit interaction. In particular, mercury-cadmium telluride is the first place where this physics was experimentally found. And what they did is they made a sandwich structure of mercury tellurides with surrounded by mercury-cadmium telluride. And this two-dimensional layer, as predicted by Bernavig, Husen, and Zhang, was found to be precisely this two-dimensional quantum spin Hall insulator, and electrical measurements then measured the electrical transport in these helical edge states, giving a conductance of 2e squared over h. Okay, and so this sort of this experiment is where these topological phases came to life in the real world. Okay, and so this was the beginning of a very exciting time in condensed matter physics. Okay, so this is a sort of a two-dimensional topological, time reversal invariant topological phase. You can also have a three-dimensional version of this. Okay, so there I can imagine I can take a two-dimensional electrical conductor. It has both upspins and downspins. And again, what I want to do is I want to split it in half in a way that preserves time reversal. And so the way you can do that is you can split it, and on the top and bottom surfaces, what you have is again, an impossible 2D time reversal invariant conductor on the surface that has what we call a single Dirac cone. Okay? And so this is something which, with time reversal symmetry, it's impossible to have in isolation. Okay? And so these two-dimensional surfaces are again, topologically protected. And so this phenomenon happens in what's called a three-dimensional topological insulator. Again, you need strong spin-orbit interaction. Bismuth has strong spin-orbit interaction. So bismuth selenide is one of the nicest three-dimensional topological insulators. And the way we can think about it is that on the inside, it's an electrical insulator. It's completely electrically inert. There's an energy gap. The electrons can't do anything. But on the surface, it has this impossible electrical conductor on the surface. Okay, and so this is a picture of the surface taken by angle-resolved photoemission spectroscopy, which basically is a way of measuring the electronic structure of the surface. And this picture shows sort of a textbook perfect looking Dirac. Topological insulators are materials that one can create in a laboratory, and there's a whole industry now of different variants on this idea. Okay, so I'm just going to flash this. Since we're in the Simons Center, it seemed appropriate to to point out that the topological invariant that characterizes a three-dimensional topological insulator actually can be expressed in terms of the Chern-Simons three form. So if you're happy with this kind of mathematics, then I don't need to explain it. And if you're not happy with it, it would take me too long to go through this. So just let me point out, though, that the topological invariant characterizing a three-dimensional topological insulator actually has a natural form expressed in terms of the Chern-Simons three form. So now what I want to do in the remaining time is I want to talk about another kind of topological phase, which is a topological superconductor. And the motivation for this is, it would be nice to be able to have a quantum computer, okay? Because, there are classes of problems that a quantum computer could do much faster than a regular computer, okay? And so that's something that would be nice to have. The problem is that making a quantum computer is hard, because quantum information, stored in bits, ones and zeros, or superpositions of ones and zeros. Superpositions are very fragile, because if you measure them, you destroy them. And so the question is, how do you keep the quantum computer from accidentally measuring itself? And so let me pose a possible solution, which is really the genius of Alexei Kitaev. We have to thank for this, which is that you have a qubit. It's a indistinguishable. It's an indivisible object. It's some two-level system. So the idea is to split it in half, in the same way that we've been splitting other indivisible things in half. So if I can have half of the qubit be at one end of a system and the other half be at the other end, then by doing a local measurement on this half, it would be impossible to measure the state of that qubit. Okay, and so if we can do this, then the quantum information will be protected from local sources of decoherence. So how can we make this happen? Okay, and so the idea here is to what's called topological superconductivity. And I don't have time to give you a whole course on superconductivity right now, but let me just make the point that superconductors can be understood using exactly the same language as insulators. Okay, so if you do the BCS mean field theory, then the superconductors can be described by a sort of a non-interacting fermion theory. The price for this sort of semiconductor picture, there's an energy gap. The price for this semiconductor picture is that the conduction band and the valence band actually have this exact particle-hole symmetry. Okay. And moreover, there's even more, though, which is that an electron in the conduction band and a hole in the valence band, they're actually redundant descriptions of the same state. Okay, and so there's adding an electron into the conduction band does exactly the same operation as removing an electron from the valence band. So that's the price you have to pay for this sort of semiconductor interpretation of a superconductor. Okay, but other than that, so one can still think about, are there topological classes for now these Bloch-Bogoliubov-de Gennes type Hamiltonians that have this intrinsic particle-hole symmetry? And the simplest version of that is in one dimension, where at the end you could possibly have a zero energy state, just like in the polyacetylene that I had. Okay, but now the particle-hole symmetry is something that's intrinsic. Okay, and so this is in fact what happens at the end of a one-dimensional topological superconductor. But now, because of this redundancy, this zero mode it's almost like half of a state. So it's a state where adding an electron into it and removing an electron do exactly the same thing. It's a state where the particle is its own antiparticle. Okay, and so this is what a Majorana zero mode is. And so if we could make these Majorana modes happen, then thanks to Kitaev, we can use them to store quantum information. Okay, and that from decoherence. Okay, and so the question is, how can we make this come to life? Okay, and the problem is you can't go to the store and buy a topological superconductor. You have to do something clever in order to make it happen. And so, but this is something where there's been a lot of progress, and a lot of ideas, and it's a very exciting time. So one of the first ideas that we had was to create topological superconductivity by using ordinary superconductors, but some topological materials. Okay, and so in particular, if you have a superconductor and a topological insulator, so if you have a three-dimensional topological insulator which has this surface state, and you put a superconductor on top, which makes the surface states themselves superconducting, then what we were able to show is that if you have a vortex in the superconductor, it hosts one of these Majorana zero modes. Okay. Likewise, if you have a two-dimensional quantum spin Hall insulator, which has the helical edge states, if you have an interface between a superconductor and a magnet, then that hosts a Majorana zero mode. Okay, so these were sort of our original ideas. Then shortly afterwards, it was pointed out that you don't even really need the topological insulator. Well, what you really need is you need to have a semiconductor that has strong enough spin-orbit interactions, and you need to be able to sort of tune that to a sweet spot. So in particular, if you so these authors predicted that if you have a semiconductor wire appropriately configured and proximatized by a superconductor, that you should be able to get these Majorana modes. And so this was the motivation for the sort of groundbreaking experiment by Leo Kauenhoven, where he made he had a semiconductor nanowire proximatized by a superconductor, and he tunneled into the end and saw this zero bias peak. And this zero bias peak is exactly what you would want to see if you had a Majorana mode there. Now, people are still fighting about whether this zero mode is explained by the interesting explanation or whether it could be explained by less interesting explanations. Okay, and I don't want to go through all of the things one has to worry about for this. There are many, but I think there's been a lot of progress in our understanding, and this is something which has really developed a long way. And and there are many other venues where this kind of thing seems to be showing up. So in ferromagnetic atomic chains on superconductors, so there are beautiful experiments by Ali Yazdani where using an STM they can sort of look at the topography, and then in the spectroscopy they see this zero energy state lighting up at the end. There are experiments on the two-dimensional mercury telluride, the two-dimensional quantum spin Hall effect, helical edge states, where they observe a kind of 4 pi periodic Josephson effect, which is something that you would expect if you had this topological superconductivity. There's also more recent experiments which are more along the lines of our original proposal of using a superconductor on a topological insulator. So they have a 3D topological insulator with a superconductor, and then they go around on the surface and tunnel into the surface. And in the presence of a vortex, they see a zero mode. Now, with these experiments, one has to be a little bit cautious about whether they're seeing whether this is really a discrete zero mode or not. And so there's some question about that. But this is promising. And the most recent, which seems to be very exciting, is a material, an iron selenide superconductor, which what it turns out to be is its electronic structure is like a combination of a superconductor and a topological insulator. So it has a surface state. In the absence of superconductivity, it has a topological insulator surface state. But then it itself is a superconductor. So it's as if the surface state is, instead of being proximatized by an outside superconductor, it's proximatized by the inside. Okay, and again, they scan around looking at vortices, and they see these nice zero modes sitting inside the vortices, and they've even been able to resolve the Caroli-de Gennes. Inside a vortex, you expect actually a set of discrete energy. Good. Okay, so all right, so I think I'm just about finished now, and so what I want to do is I want to just sort of tell you a little bit about what directions this field is going, because there are different directions one can go in, and they're all interesting. So one sort of vast frontier is that there are many, many more examples of topological band phenomena. So this is the phenomena where I'm thinking about the sort of single particle quantum mechanics of energy bands that can have topological, a character to them, and in particular, one can explore the roles that different kinds of symmetry play. And so let me just give you an example of this, which and so perhaps you've heard of graphene, which is a single two-dimensional plane of carbon atoms, and the thing that's interesting about graphene, it has a conduction band and a valence band, but they exactly touch each other at these two distinct Dirac points. Okay, and so you can ask the question, what is it about graphene that makes it have this Dirac point? Okay, and in fact, it was actually this question that was the question that got me started on this whole thing, 15 years ago. But the answer to that question really is that it's a combination of symmetry and topology. Okay, because so graphene has symmetries. It has inversion symmetry. It has time reversal symmetry, and it also has spin rotational symmetry. To first approximation, graphene has no spin orbit interaction. Okay, and so these combination of symmetries are enough to protect the degeneracy that occurs at the Dirac points in graphene. Okay, so what we can call graphene is a symmetry-protected topological semimetal. Okay. Now, so actually, the thing about graphene, it has these Dirac points, but there are actually 4 of them. Okay, so because there's 2 valleys, there's the K and K prime valleys, and each valley has either up or down spins. So really, it's a Dirac to the 4th. Okay, and so you can ask the question, could I have a two-dimensional Dirac semimetal, a two-dimensional semimetal that has fewer Dirac points? Okay, so could I just have 2? Okay, and it turns out that is impossible. Okay, it is impossible to have a symmetry-protected two-dimensional system with a single pair of Dirac points. Okay, that is impossible for sort of the same reason it's impossible to have just a purely a single chiral edge state. Okay, but it should be possible on the boundary of some kind of topological phase. And so this is a topological phase that we find. And this was a collaboration with Andre Bernovig and also Jen Cano, where we found that there exists a 3-dimensional symmetry-protected topological phase that we call the topological Dirac insulator, where it basically does this splitting the indivisible, putting a single pair of Dirac points on the surface, and these Dirac points are protected by a kind of interesting kind of symmetry called a non-symmorphic symmetry, which is basically the symmetry of this pattern of wallpaper, and it has some interesting symmetries in it. Okay, so these are just an example. There's a huge amount of activity going on because in this field, there's a strong interaction between the sort of theory and also computation, because you can compute the band structures of materials, and when band theory works, it works really well. Okay, and between theory, computation, and experiments, there are many real materials that have these phenomena, and so this is a whole field of physics right now. Okay, so this is one direction you can go in, and let me just close by pointing out that there's another direction as well, which is more along the lines of thinking about the sort of many-body interpretation of these things. Okay, so the frontier of states combining topology and strong interactions. So let me just give you a couple of examples of this. And again, I want to think out that we have this one-dimensional chiral Dirac fermion. Okay, we got that by splitting the right movers apart from each other. But can I split this further? Okay, and so it turns out that this Dirac fermion can be composed into two Majorana fermions. Okay, and in the presence of superconductivity, this is how topological superconductors work. In the presence of superconductivity, without superconductivity, they're glued to each other. They can't separate. But in the presence of superconductivity, you can split them apart. Okay, and so this takes this Dirac fermion, which has a chiral central charge, which is rated to the thermal conductance of C equals 1. It splits 1 into 1/2 plus 1/2. Okay, so that's one version of this, and we may be on the way now to having these kinds of topological superconductors. So this is not completely crazy. Okay, now let me tell you something that's a little bit more crazy, which is, so now we have this chiral Majorana edge state. Can we split it further? Okay, and I don't know how to split a single chiral Majorana fermion, but if you give me 7 of them, then in principle, I do know how to split it. So let me just imagine, so humor me for a little while, that I have 7 copies of a topological superconductor with C equals 7 halves. Then this C equals 7 halves factorizes in the same way that C equals 1 factorizes. It factorizes into 7/10 and 14/5. And so these theories are non-trivial conformal field theories. One of these is related to the tricritical Ising model. The other one is related to G2 level 1. Okay, and so this factorization happens. And so if you're a Majorana fermion coming along here, then you split into a pair of Fibonacci anyons. Okay, and so this is and so the question is can we make these Fibonacci anyons come to life? And there are reasons that this would be a desirable thing to do. This is a little bit more further down the horizon, though, in terms of reality. And so the current status is that there's been a lot of theoretical progress in terms of understanding what kinds of things might be possible. But much more work needs to be done in order to figure out how to make these kinds of proposals closer to reality. Okay. All right. So let me just finish up. So these ideas of symmetry and topology are a very powerful framework for discovering sort of new phases of matter. I told you about some of them. There are many experimental challenges in this field, and many theoretical challenges as well. And so this is a very exciting time to be in condensed matter physics. So thank you very much.
I think it's great to think about the qubit, the split into the irons, but how many qubits can you put together? I mean, experimentally.
Oh, not for... Well, let me just, you mean these topological qubits? Well, at this point, I think I can confidently say 0. So look, where we are experimentally right now is all of these experiments are just observing the 0 mode. So it remains to demonstrate that these Majorana 0 modes are capable of storing quantum information. I mean, just tunneling into it, you're not probing the state. Okay, so we don't even have a qubit yet. Okay, so now I don't know. I can use my imagination to imagine once you get the qubits and you have ways of manipulating them, maybe you could scale it up. But that's sort of an engineering problem that I don't feel qualified to be a pessimist about.
Is this G2 and the tricriticalizing is accidental, or is somehow related to the fact that there is something called G2 superconformal algebra which contains inside the tricriticalizing?
Maybe. I'm not sure I understand fact that this was based on, which is that if you take SO7 level 1. There's a coset of SO7 level 1 divided by G2 level 1, and that is precisely the tricriticalizing model. So SO7 level 1 divided by G2 level 1 somehow has the superconformal symmetry that the tricriticalizing model has. But that's as deep as I know how to go. Okay. Yeah. I mean, this is the kind of thing I know that you guys understand much better than I do. I'm still a beginner at this.
The that you just mentioned, though, the concept appears in
yes.
superconformal.
Well, and we learned it from you guys too. I mean, that's in fact, I have to say, I didn't, when we started on this, I didn't even know what G2 was, but I have a student who had we knew about cosets, and we knew that I could use cosets to do constructions like this. And so I had a student who had the courage to read papers by Kumram Vafa that taught us these things. So
this is my paper.
Is it? Oh my gosh. Okay, so you see, I profess my ignorance, but yeah.
There is another one which is very fascinating, which is there is a spin 7 version of it, and then it comes together with Ising.
Okay.
So Ising goes with spin 7, and G2 goes with tricritical Ising.
Okay.
In the same construction.
Okay. I think I have some things I could learn from you.
Maybe it's somehow Ising case knows something about spin 7 there.
Okay. Okay. Good.
Can you iterate the Fibonacci?
What's that?
Fibonacci normally has a sequence that goes all the way to infinity, right? Fibonacci is a sequence.
Yes.
Many way of this, right? Because you can have more Fibonacci decompositions.
Oh, you mean go further? You mean split the Fibonacci? Yeah, I don't know. Yeah, I got that. Yeah, I don't know. Yeah.
Last question.
But how to get all 7 in the first one?
7 copies of seven topological superconductors.
Ah.
So these are this. I mean, in principle, if we in principle having this C equals 1/2 is possible. And there was even a recent experiment that claimed to have had evidence for making this happen. So basically, what they did is they took a quantum Hall state and proximatized it with the superconductor and claimed that they had experimental evidence that it had split into 2 Majoranas. Okay, now I think this experiment may not be surviving, so that's the reason I didn't want to bring it up. But it's not. I mean, the idea that this experiment should be possible is reasonable. And so all I'm doing is I'm making 7 of them.
Did anyone try
Odd
three
number.
copies of that?
What's that?
Odd number. At the beginning you get even number.
No, but you have to. It's possible to separate them. Okay, so can I? Can I turn one of these up so I can get on the chalkboard?
Just a second. Why don't you do it?
So the split them so that I just have this. So I just